Previously on Physicsball Z, our heroes discovered the differences between direct and alternating currents. And just when they were able to disable the fuse in the enemy's circuit, they were attacked by this past paper question. However, with the power of the ancient highlights manifesting themselves through the grace of science, they were able to pattern this question. And now, our heroes have finally infiltrated the national grid in the enemy's front line. Will our heroes step up to this challenge and get the work done, or will they step down and bow down in disgrace? Find out in today's episode of Physicsball Z. Here are the retrieval questions for this lesson. You know what to do. The outer casing is made from a hard plastic. This is because it's an electrical insulator. The pins are made from the alloy brass, which is a strong electrical conductor. Acids give out hydrogen ions, alkalis give out hydroxide ions. The AR of carbon is 12, that's its mass number, the massive number on the periodic table. And the MR of carbon dioxide is 44 because you add up the mass of one carbon to 2 oxygen atoms. Before we move on to the national grid, let's quickly recap power. From my video on power, you'll remember that we have these 4 equations to memorize. Work done over time, energy over time, current times potential difference, and current squared times resistance. Notice that when we have time and power in the calculation, they are both at the bottom. And when we have power and current, power is on top and current is at the bottom. Work done and energy are both measured in joules. Power is in watts and time is in seconds. Current is in amps, potential difference is in volts, and ohms is resistance. Those are the units for all of this, okay? Now let's look at this question. We are asked which of these two is using more energy. A 1 kilowatt heater used for 1 hour or a 2 kilowatt heater used for 30 minutes. Have a think. Which of these equations are we gonna use and then calculate the thing? We're calculating energy and we have both power and time, which means we're using this equation here. We need to rearrange this equation to work out energy transferred. But notice that our units are off. 1 kilowatt is 100 watts. And for hours, we need to times 60 seconds by 60 minutes, which gives us 3,600 seconds in 1 hour. We now multiply to give us a value of 3.6 million joules. Doing the same thing for the other heater, we have 1,800 seconds in 30 minutes. 2,000 watts times 1,800 gives us 3.6 million joules. So both of them have the same amount of energy used. All fossil fuel power stations have the same generic mechanism. Look very carefully at what is being pumped into this turbine. This motion is moving along this axis here. Use these images to answer these challenge questions. The generator generates electrical energy. We can see that electricity just flashing over there. Over here, we see the same thing that's coming out of the kettle is also going into the turbine. So steam is what's being used to turn the turbine. For the mega challenge, the fuel in the power station heats up a liquid, and that liquid must be water. This is what causes the steam. The water is being heated up, which turns into steam and turns a turbine, which turns a generator, generating electricity. So let's summarize this. The fuel heats up a boiler containing water. This fuel could be coal, oil, etc. The water turns into high pressure steam. This steam turns a turbine. The turbine turns a generator, and the generator generates electricity. Let's look at some energy transformations at each of the stages I just showed you. In the boiler, we burn a fuel and create steam from water. Pause the video and deduce what the input and output energies must be at this stage. The chemical energy from the fuel is being transformed into thermal energy. So we had thermal energy. What is then transferred to the steam that helps it turn the turbine? The steam has kinetic energy, and that's what's used to turn the turbine. Finally, the turbine turns a generator to produce a current. Try and work out the input and output energies here. The input is kinetic and the output is electrical. Here's the setup for the national grid. We have a power station and cables that run along up to what we call a step-up transformer. These metal things here are pylons, and we have a step-down transformer and then your house. Here are the potential differences at each stages in the national grid. This seesaw is representing the relationship between current and potential differences in these transmission cables. And down here, I'm showing you what happens when the potential difference is low and the current is high. This is what can happen there, so look very carefully what's going on. And of course, here are some challenge questions for you to have a go at. Step-up transformers increase potential difference and step-down transformers decrease potential difference. Extrapolating from this image, when the potential difference increases, the current decreases. And looking at this high current wire, the wasted energy is thermal energy. We can see it smoking up because it's actually getting very hot. This is why step-up transformers increase the potential difference. This is to decrease the energy that's wasted along the transmission cables. Based on all of that now, see if you can match up the function of each part of the national grid. Step-up transformers increase potential difference, decreases current, which means less wasted energy. Transmission cables have low resistance material, reducing heating, and this reduces wasted energy. Step-down transformers reduces potential difference, increases the current, and makes it safe to be used in the house. And there we go. Mission complete.
Fatality.
Check the descriptions, check the timestamps, go back where you need to go. I'll catch you guys in a bit.